For centuries, black holes have reigned in human imagination as the ultimate cosmic predators, mysterious and terrifying entities that devour everything drawn too close. They are the dark engines of the universe's wildest legends, immense gravitational traps that crush stars, bend light, and twist time until it nearly breaks. Within their invisible boundaries, even the fastest thing in existence, light itself, cannot escape. They have been portrayed as bottomless voids, regions of infinite density where the laws of physics collapse into silence. Yet the deeper science peers into their nature, the more unsettling questions arise. Are these celestial monsters truly the final word in gravitational extremes, or could the universe be hiding something stranger still? Something that mimics the look of a black hole, but hides a completely different heart? What if these cosmic abysses are not tombs, but illusions concealing a new kind of object that challenges everything we think we know about space, time, and death itself? Among the many ideas that have emerged from modern theoretical physics, few are as bold or captivating as the concept of the gravitational vacuum star, better known as the gravastar. The very name sounds like something pulled from science fiction, yet it represents one of the most serious attempts to rethink what happens when a massive star dies. A gravastar appears at first glance to be just another black hole. From the outside, it exerts the same irresistible gravitational pull, bending starlight and devouring nearby matter in much the same way. But beneath that deceptive exterior lies something profoundly different. Unlike a black hole, which hides a singularity, a point where density becomes infinite, a gravastar's core is thought to be filled with a mysterious form of energy, an invisible sea of what physicists call vacuum energy. Surrounding this core is a thin, ultra-dense shell made of exotic matter, unlike anything found in ordinary atoms. This combination, according to the theory, prevents the star from collapsing entirely, creating an object that hovers on the edge of becoming a black hole, but never quite crosses that boundary. The result is something that looks like a black hole from afar, but is, in essence, an entirely new kind of structure. To the human mind, trained to see the cosmos in terms of clear beginnings and ends, this idea is deeply unsettling. Black holes have long represented the end of the road, a one-way journey into nothingness. They are where stars go to die, where the story of matter ends and even light is lost to eternity. But gravastars propose a different kind of ending, one that might not be an ending at all. If they exist, they could preserve the information that black holes supposedly erase, potentially solving one of the biggest paradoxes in modern physics. They would be, in a sense, the universe's way of keeping its own secrets safe, hidden behind a facade of darkness. To appreciate just how revolutionary this concept is, one must first understand the mythology and science surrounding black holes themselves. The very idea of an object so dense that nothing can escape its pull dates back to the 18th century, when thinkers like John Michel and Pierre-Simon Laplace speculated about dark stars, whose gravity would trap even light. These early musings were largely forgotten until Albert Einstein's general theory of relativity revived the notion in the early 20th century, providing the mathematical foundation for such bizarre entities. Over the decades, black holes evolved from abstract equations into real astrophysical players, observed indirectly through their influence on nearby stars and gas. Yet, even as evidence for their existence mounted, the singularity at their core, the point where gravity becomes infinite and time ceases to exist, remained an uncomfortable problem. Infinity in physics is a red flag, a sign that our understanding is incomplete. Gravastars were conceived as a way to escape that mathematical dead end. They replace the infinite with the finite, the unknowable with something that can, at least in principle, be described. In this sense, they represent both a critique of black hole theory and an evolution of it, a proposal that perhaps the universe does not tolerate infinities after all. The notion that a collapsed star could halt just short of forming a singularity and instead stabilize into a strange equilibrium of vacuum energy and exotic matter might sound fantastical, yet it fits elegantly within the framework of known physics. It takes the mathematics of relativity and extends it, adding layers of quantum reasoning and cosmological insight. If black holes are the monsters of the cosmos, born from chaos and finality, then gravastars are the trickster's objects that imitate the darkness but hide light within. They embody one of the most important lessons of science, that even our most terrifying ideas can evolve into something subtler and more beautiful when we look closer. So as we embark on the journey to understand these mysterious entities, it's worth asking whether the black holes that haunt our universe are truly what we think they are, or whether they're disguises for something far more extraordinary. Perhaps what we've been calling the end of everything is really just another beginning, waiting to be understood. The idea that the universe's most mysterious objects might not be what we think began to take shape at the start of the 21st century, when a few physicists started to question whether a collapsing star must always end in a black hole. For decades, this had been taken as a near absolute truth. The story was simple. When a star many times more massive than the Sun exhausts its nuclear fuel, gravity takes over completely, crushing the star's core beyond any possibility of resistance. According to Einstein's equations, there comes a point where no known force can counteract the inward pull, and the collapse continues until everything is squeezed into a singularity of infinite density hidden behind an event horizon. For most of the scientific community, this was the final chapter of stellar evolution. Yet in 2001, two theoretical physicists, Pavel Mazur and Emil Motola, dared to ask if nature might have another way. They proposed that perhaps the collapse of a massive star doesn't inevitably end in a singularity at all. Instead, under certain extreme conditions, it might transform into something completely different, a stable configuration in which the inward pull of gravity is balanced not by ordinary matter, but by the repulsive pressure of vacuum energy. Their hypothesis was more than just a mathematical curiosity. It was a radical challenge to the conventional picture of cosmic death. Mazur and Motola imagined that as a star implodes, a quantum phase transition could occur inside it, similar in spirit to how water turns into ice or vapor. This transition would convert the collapsing matter into a form of vacuum energy, halting the collapse just before a singularity could form. What remained would be a kind of cosmic bubble, a sphere of vacuum energy sealed within a thin layer of ultra-dense exotic matter. To an outside observer, the object would appear nearly identical to a black hole, possessing a gravitational field so intense that even light could barely escape its grasp. Yet inside it would be entirely different, a smooth, finite structure without a singularity, without an event horizon, and without the paradoxes that have long haunted black hole theory. This proposal didn't emerge from nowhere. It was born from decades of tension between two pillars of physics, general relativity and quantum mechanics. Einstein's theory describes gravity and the large-scale structure of the universe, while quantum mechanics governs the microscopic realm of particles and energy. Both have been tested to extraordinary precision, yet they remain fundamentally incompatible. The singularities predicted by relativity are points where density and curvature become infinite, which quantum theory says cannot exist. The laws that govern atoms and subatomic particles break down in the presence of such infinities. Mazur and Motola's idea offered a possible bridge. By introducing vacuum energy, a quantum concept, into the framework of general relativity, they showed how a collapsing star could reach an equilibrium instead of tearing itself apart. Their gravitational vacuum star, or gravastar, would be a hybrid creature, part classical and part quantum, representing a step toward the elusive union of the two great theories. When they published their paper, it attracted both curiosity and skepticism. Some hailed it as a bold and imaginative step that could resolve long-standing paradoxes, while others dismissed it as speculative. But even those who doubted the specific details recognized that it touched a nerve in modern astrophysics. The black hole, once seen as the perfect endpoint of collapse, had become an embarrassment of infinities and contradictions. It violated basic principles of information conservation, suggesting that whatever falls in is erased from the universe forever, something quantum physics refuses to accept. The gravastar model, by contrast, preserved the integrity of information and offered a physical structure that could, at least in principle, be described without invoking the impossible. It was a way of saying that maybe the universe doesn't truly create infinities. Maybe it always finds a balance, even at its most extreme edges. In the years that followed, the term gravastar began to circulate quietly in theoretical discussions. It didn't overthrow the black hole overnight, but it opened a door. It reminded scientists that the most accepted ideas are still just models, approximations of truth. It also reignited a deeper philosophical question. Does the universe really allow total collapse, or is there always something that stops the fall? For Mazur and Motola, the idea wasn't about replacing black holes entirely, but about expanding the range of what's possible. Nature, they suggested, might create both. Some massive stars could collapse into true black holes, while others might freeze into gravastars depending on their conditions and composition. This possibility added new richness to our understanding of cosmic evolution. It implied that the universe might be filled with invisible imposters objects masquerading as black holes, but with completely different interiors. Detecting them would be extraordinarily difficult, because from the outside their gravitational signatures would be almost identical. Yet the distinction, if ever proven, would rewrite our cosmic story. It would mean that the supposed monsters of the universe are not all what they seem. The origin of the gravastar idea was, therefore, more than a theoretical exercise. It was an act of rebellion against resignation, the refusal to accept that the universe ends in infinities and paradoxes. It was a reminder that physics, at its heart, is not just a set of equations but a way of asking deeper questions about existence itself. Mazur and Motola's work planted a seed of doubt, and with it, the possibility of a new kind of cosmic object that could one day change how we understand the very structure of reality. To understand why the gravastar concept is so fascinating, one must first look closely at how it differs from a black hole, not just in theory but in essence. At a glance, both seem indistinguishable. Each exerts a gravitational pull so strong that any nearby object, from dust to starlight, is drawn inward with no hope of escape. Each appears as a dark sphere surrounded by a halo of brilliant radiation from matter spiraling toward oblivion. To most instruments, these cosmic shadows look identical, yet their internal structures could not be more different. The distinction lies in what happens just beyond that invisible threshold, where gravity's grip becomes absolute. In a black hole, this boundary is called the event horizon, a surface marking the point of no return. Once anything crosses it, there is no possible path back into the observable universe. Inside, space and time trade roles. The inward direction becomes as inevitable as the passage of time, drawing everything toward the singularity at the core. There, according to general relativity, density becomes infinite, and the known laws of physics lose all meaning. It is a region not merely hidden from view, but removed from reality as we understand it. The gravastar, on the other hand, has no such singularity and no true event horizon. Instead, it possesses a physical surface, a boundary of ultra-dense exotic matter that halts collapse and separates the internal vacuum core from the external universe. Where the black hole swallows light, the gravastar reflects or absorbs it in complex ways, depending on the properties of its shell. To an observer far away, the difference would be nearly impossible to detect, because the gravastar's surface lies so close to where an event horizon would be that its gravitational field distorts light in nearly the same way. But conceptually, the two objects inhabit entirely different categories of existence. In a black hole, the singularity represents a breakdown of reality, a point where space and time cease to have meaning. In a gravastar, by contrast, space-time remains continuous, smooth, and finite all the way to the center. The inner region is filled not with infinite density, but with vacuum energy, an exotic state of space itself, exerting outward pressure that counterbalances gravity's inward pull. The result is equilibrium, a kind of cosmic stalemate between collapse and expansion. If one could somehow peer inside, one would not find a crushing abyss, but a strange, serene, void, silent, weightless, yet dense with energy. This difference, though invisible, carries profound implications for physics. It suggests that nature may avoid singularities altogether, maintaining order even in its most violent processes. It also changes the story of what happens to matter and information that falls inward. In a black hole, all traces of the past are lost beyond the horizon. In a gravastar, there is no true inside from which escape is impossible, only layers of structure where information might persist in some form. The gravastar's surface functions almost like a cosmic mirror, preserving information that would otherwise be erased. Such an idea directly challenges one of the greatest unsolved mysteries in modern physics, the black hole information paradox. If information cannot be destroyed, as quantum mechanics insists, then the classical black hole model must be incomplete. Gravastars offer an elegant way out. They mimic the external behavior of black holes so closely that they could explain all current observations, yet they do so without invoking infinities or information loss. They are in effect a reconciliation between the two great languages of physics, the geometric determinism of relativity and the probabilistic subtlety of quantum theory. The inside-outside difference also changes how we imagine time itself. In a black hole, time ends at the singularity. There is no future beyond that point. In a gravastar, time continues smoothly throughout the structure, even though the interior may behave in radically unfamiliar ways. The vacuum core is not empty in the ordinary sense. It teems with quantum fluctuations and energy fields that defy intuition. It may be more accurate to think of it as a different phase of the universe, a region where the fabric of space behaves more like a fluid than a solid framework. In this sense, a gravastar is not just an alternative to a black hole, but a window into a deeper understanding of space-time itself. The comparison between the two objects is like that between a shadow and the thing that casts it. Black holes are the idealized limits of Einstein's equations, perfect in their simplicity but physically unattainable if infinities are truly forbidden by nature. Gravastars, by contrast, are imperfect, messy, and real objects that approximate the ideal without ever crossing into impossibility. They remind us that physics is not just about the extremes of mathematics, but about the balance between what can exist and what cannot. The distinction between a black hole and a gravastar is thus more than a technical detail. It is a philosophical divide. One represents a universe that tolerates infinities and absolute boundaries, where things vanish beyond recovery. The other represents a universe that bends but never breaks, that hides its mysteries behind layers of complexity rather than erasing them. From this perspective, the gravastar can be seen not as a denial of the black hole's existence, but as its reinterpretation, an assertion that even in the darkest corners of reality, something remains. Perhaps the true lesson of comparing the inside and outside of these objects is that the universe is not as absolute as it appears. There may always be hidden structures beneath what looks like finality, subtle patterns where we once saw chaos, and quiet continuities where we expected an end. At the heart of modern physics lies a contradiction so profound that it exposes the limits of human understanding. On one side stands general relativity, Einstein's grand description of gravity as the curvature of space-time, a theory of breathtaking elegance that explains the motion of planets, the bending of light, and the birth of the cosmos itself. On the other side stands quantum mechanics, the rulebook of the subatomic world, where uncertainty, probability, and energy fluctuations dominate. Each theory is immensely successful in its own realm, yet when they meet in the crushing depths of a black hole or the first moments after the Big Bang, they clash violently. The singularity predicted by relativity represents the ultimate failure of this union, an infinitesimal point where gravity becomes infinite, time stops, and the known laws of physics disintegrate. Such infinities are not physical realities, but mathematical breakdowns, signs that our equations have reached a limit beyond which they no longer describe nature. The universe, as experience tells us, abhors infinities. Everything observable, from atoms to galaxies, exists in finite quantities, bound by measurable limits. The singularity, therefore, is not a triumph of understanding, but an admission of ignorance. The gravastar theory arises from the desire to replace that mathematical abyss with something physically meaningful. It proposes that the collapse of a massive star never truly reaches infinite density. Instead, as the matter compresses and the internal pressure soars, quantum effects become dominant. The energy of the vacuum, normally invisible and negligible, suddenly takes center stage. According to quantum field theory, empty space is not truly empty, but seethes with virtual particles and fluctuating energy fields. This background energy, known as vacuum energy, is thought to exert a repulsive pressure, the same mysterious force believed to drive the accelerated expansion of the universe. In the gravastar model, this vacuum energy forms a bubble at the star's core, counteracting gravity's pull and preventing total collapse. The result is a stable, finite object rather than an infinite singularity. This elegant solution not only removes the problem of infinities, but also aligns with the broader picture of cosmic evolution, where vacuum energy is already known to play a crucial role on the largest scales. By invoking this same principle at the smallest and most extreme level, the gravastar connects cosmology and quantum physics in a single conceptual bridge. The black hole, by contrast, remains a paradox wrapped in beauty. It predicts phenomena that can be observed, such as gravitational waves and accretion disks, but hides its ultimate truth behind a horizon we cannot penetrate. Inside that horizon, time and causality unravel. For decades, physicists have tried to tame this chaos with the tools of quantum gravity, string theory, and loop quantization, yet no approach has fully resolved the singularity problem. The gravastar's appeal lies in its simplicity. It requires no new dimensions, no speculative strings, only the recognition that vacuum energy and quantum pressure could intervene before the catastrophe completes. It takes the equations of relativity and modifies their boundary conditions, replacing the infinite with the calculable. In doing so, it restores continuity to the fabric of the universe. Still, simplicity does not guarantee truth. The gravastar theory raises its own questions. How exactly does the transition from normal matter to vacuum energy occur? What physical mechanism triggers this sudden change inside a collapsing star? Could the process be observed indirectly through gravitational waves or radiation patterns? And most importantly, if singularities do not exist, why have we never seen clear evidence of these alternative structures? These uncertainties keep the theory at the edge of speculation, a daring hypothesis waiting for its observational test. Yet even as an unproven idea, it serves a vital role. It challenges the complacency of accepting infinities as part of nature. The history of science shows that every time we encounter infinity, it signals a gap in our knowledge, a hint that a deeper theory waits beneath. The ultraviolet catastrophe in classical physics, for example, once predicted infinite energy from blackbody radiation until quantum mechanics resolved it. Likewise, the notion of infinite density in black holes may be a sign that our understanding of gravity itself requires revision. Gravastars, by removing the singularity, offer a glimpse of what that revision might look like. They suggest that space-time could have a built-in resistance to absolute collapse, a kind of quantum elasticity that prevents it from tearing apart. This would mean that even in the most extreme conditions, the universe retains its coherence, refusing to reduce reality to nothingness. The physics problem, then, is not merely about equations, it is about meaning. What does it really mean for time to end, for space to vanish, for information to be destroyed? These are not just mathematical puzzles, but philosophical challenges to the very idea of a lawful universe. The gravastar is one attempt to answer them, not by rewriting the laws of nature, but by showing how they might protect themselves from contradiction. If black holes represent the point where our theories collapse, gravastars represent the possibility that they can be repaired. Whether they truly exist or not, their value lies in how they force us to rethink the boundaries of the possible. They remind us that infinity is not a destination, but a signpost and indication that we are standing at the edge of known physics, peering into a realm that still defies comprehension. Among the many enigmas surrounding black holes, none has provoked more debate than the information paradox, a puzzle that cuts to the core of physics itself. The paradox arises from the collision of two fundamental principles. On one hand, general relativity tells us that anything falling into a black hole disappears beyond the event horizon, cut off from the rest of the universe forever. On the other hand, quantum mechanics insist that information can never be truly lost. Every particle, every field configuration carries unique quantum data, and the total information of a system must remain conserved. If black holes really destroy the information they consume, then one of the two greatest theories in science must be wrong. This contradiction has haunted physicists for half a century, leading to countless arguments, thought experiments, and radical proposals. Stephen Hawking's discovery of black hole radiation in the 1970s made the situation even more puzzling. According to his calculations, black holes emit faint thermal radiation due to quantum effects near the event horizon. Over enormous timescales, this radiation causes the black hole to lose mass and eventually evaporate completely. Yet the radiation itself is purely thermal. It contains no trace of the information that fell in. If the black hole disappears and the information is not encoded in its radiation, then the data about everything that crossed the horizon is gone forever. This outcome would shatter the foundation of quantum theory, which demands that information, while it can change form, can never vanish from the universe. For decades, this paradox has stood as one of the deepest unsolved problems in theoretical physics. Various ideas have been proposed to resolve it, some suggesting that information leaks out subtly through quantum correlations in Hawking radiation, others arguing that it remains trapped in a hidden remnant, or that the very concept of an event horizon might be flawed. It is in this context that the gravastar enters the conversation as a potential bridge between the classical and quantum worlds. By design, a gravastar has no event horizon, and therefore no absolute point of no return. Matter and energy approaching its surface encounter an extreme but finite barrier, one that may absorb, reflect, or re-emit radiation without erasing its underlying information. The structure of the gravastar allows for quantum coherence to be maintained, meaning that the information could, at least in principle, be preserved within the shell or re-emitted through subtle interactions with the surrounding space. In this picture, what we perceive as a black hole's thermal glow might instead be a form of information processing, a cosmic feedback mechanism rather than an irreversible burn. The vacuum energy inside a gravastar adds another layer of intrigue. In quantum field theory, the vacuum is not a void but a dynamic entity, teeming with fleeting virtual particles and fields. This restless background carries the potential to store information in non-classical ways, through correlations and entanglement patterns that transcend ordinary matter. If the core of a gravastar consists of such vacuum energy, then it might serve as a vast quantum reservoir, preserving the identity of everything that once fell toward it. Information would not vanish but be transformed, encoded into the quantum state of the structure itself. This possibility offers a graceful reconciliation between relativity's geometry and quantum mechanics' insistence on unitarity, the conservation of information in all physical processes. To many physicists, this is more than just a mathematical curiosity. It represents a philosophical shift. The gravastar embodies a universe that conserves meaning, even in its darkest places where destruction gives way to transformation. Instead of a one-way fall into oblivion, the end of a star might lead to a kind of quantum rebirth, where the data of its existence continues in a new form. In this view, the cosmos is not a machine of annihilation but of preservation, a system that hides information rather than erasing it. Such an interpretation aligns with emerging ideas in quantum gravity, holography, and information theory, all of which suggest that the universe's most extreme environments could act as information storage systems. The holographic principle, for instance, proposes that all the data within a region of space may be encoded on its boundary, a concept perfectly suited to a gravastar, whose thin shell separates two radically different domains. In this framework, the shell could act like a cosmic datasheet, encoding everything that interacts with it in the form of quantum correlations. The gravastar thus becomes more than an exotic object. It becomes a bridge, a living link between the deterministic fabric of relativity and the probabilistic tapestry of quantum theory. It transforms the black hole's fatalism into a story of continuity. No longer does the universe need to choose between geometry and information. Both can coexist within the same object, each shaping the other. The black hole paradox, which once symbolized a crack in the foundation of physics, might instead be a doorway to a deeper synthesis. Perhaps the universe itself avoids such contradictions not by breaking its laws, but by finding new configurations that honor them all. Gravastars may represent that reconciliation in physical form, a testament to the idea that the universe preserves its memory even when it seems to lose everything. And if one day observations confirm their existence, they will stand as proof that what we call destruction is often just transformation written in a language we have not yet learned to read. When Pavel Mazur and Emil Motola introduced the idea of the gravitational vacuum star in 2001, they were venturing into one of the most forbidden territories of theoretical physics, the heart of the black hole. Their paper was not an act of rebellion but an act of imagination, a bold attempt to answer questions that had haunted science for decades. Both physicists were well aware that the singularity at the core of a black hole was not a real feature of nature, but a symptom of our incomplete understanding. To them, the infinite density predicted by general relativity was less a physical object than a cry for help from the equations themselves. Something, they believed, had to intervene before that mathematical collapse could occur. The world of physics at the turn of the century was already grappling with the tension between relativity and quantum mechanics. Cosmologists were struggling to explain the mysterious force driving the accelerated expansion of the universe, soon to be known as dark energy. while particle physicists were wrestling with the implications of quantum fields and vacuum fluctuations. In this climate of conceptual turbulence, Mazur and Mottola asked a simple but revolutionary question. Could the same vacuum energy responsible for cosmic acceleration also play a role in preventing gravitational collapse? Their answer became the foundation of the gravastar model. They imagined that as a massive star collapsed under its own gravity, the compression could reach a threshold where a phase transition occurred, much like water freezing into ice, but at a scale far beyond human comprehension. Instead of forming a singularity, the matter at the core would transform into vacuum energy, a substance with negative pressure that resists compression. This vacuum bubble would expand outward until it reached equilibrium with the star's remaining mass, forming a stable, self-contained structure bounded by a thin shell of exotic matter. From the outside, this configuration would look almost identical to a black hole, but its interior would be entirely different. Smooth, finite, and free from infinities. When the two scientists first presented their idea, it was met with skepticism bordering on disbelief. Black holes were not merely theoretical curiosities by then, they were the bedrock of modern astrophysics. Observations of X-ray binaries, quasars, and galactic centers had all but confirmed their existence. To challenge their inevitability was to question decades of accumulated evidence and intuition. Yet Mazur and Mottola were not denying the reality of what astronomers saw, they were reinterpreting it. Their argument was subtle. The objects observed in space might still appear as black holes, but their interiors could be something else entirely. What we call a black hole, they suggested, might simply be the visible mask of a gravastar. It was a radical idea cloaked in familiar mathematics. Their theory preserved the predictions of general relativity on large scales, while modifying the interior solution where relativity breaks down. By introducing the quantum properties of vacuum energy into the heart of gravitational collapse, they bridged two domains that had long been incompatible. The result was a model that could, at least in principle, explain all observed phenomena associated with black holes without invoking singularities or event horizons. In the early years after their publication, the scientific community treated the concept as an intriguing speculation rather than a paradigm shift. Some dismissed it as a mathematical curiosity without empirical support. Others saw in it the glimmer of a future synthesis. A few physicists even attempted to expand the model, exploring its stability, thermodynamics, and gravitational wave signatures. The theory soon became a kind of intellectual testing ground, a place where ideas about quantum gravity, cosmology, and information theory could meet. Even its critics admitted that it elegantly exposed the limitations of current understanding. By proposing an alternative that avoided infinities, Mazur and Mottola had done what science at its best always does. They had reminded the world that no theory, no matter how successful, should be treated as sacred. Behind the academic details lay a deeper narrative about how scientific revolutions begin. Great shifts in understanding rarely start with grand experiments or dazzling proofs. They begin with doubt, with someone daring to ask whether the accepted story is complete. The birth of the gravastar theory was one such moment of intellectual courage. It showed that questioning the foundations of even the most established idea could lead to new insight. Over time, the gravastar entered the broader conversation about quantum gravity, wormholes, and other exotic compact objects. It joined a growing family of hypotheses attempting to describe what happens when matter collapses beyond the limits of conventional physics. Each of these models, whether ultimately correct or not, contributes to a larger effort to unify the cosmic and the quantum, to show that the universe is a coherent whole rather than a patchwork of incompatible rules. Mazur and Mottola's gravastar, born in the margins of theoretical speculation, became a symbol of that effort, a reminder that progress often begins where certainty ends. It may not yet have the experimental confirmation that turns an idea into a law, but it has already achieved something equally important. It has expanded the imagination of science. It has given physicists a new way to think about collapse, energy, and the limits of reality itself. In that sense, the birth of the gravastar theory was not merely the introduction of a new model, but the reopening of an ancient question. How far can matter fall before the universe says, no further? To understand why the gravastar idea emerged at all, one must return to the early history of black holes themselves and the long, uneasy relationship between theory and belief that surrounded them. When Albert Einstein first published his general theory of relativity in 1915, it revolutionized the understanding of gravity. Space and time, he declared, were not passive backgrounds but dynamic entities, bending and stretching in response to mass and energy. Soon after, a young German physicist named Karl Schwarzschild found an exact solution to Einstein's equations describing the gravitational field outside a spherical mass. This solution implied that if enough matter was squeezed into a sufficiently small volume, gravity would become so strong that even light could not escape. Einstein himself, however, was deeply skeptical. He regarded the idea of such an object as a mathematical curiosity rather than a real, physical possibility. To him, nature was too elegant, too balanced to allow such absurd extremes. His doubts were shared by most of his contemporaries, who could not imagine a star collapsing completely under its own weight. For decades, the Schwarzschild singularity remained an obscure curiosity buried in textbooks, mentioned more as a theoretical boundary than a tangible phenomenon. It wasn't until the 1930s that the idea began to stir again, when astrophysicists Subrahmanyan Chandrasekhar and Robert Oppenheimer explored the fate of massive stars. Chandrasekhar's calculations revealed that beyond a certain mass, a white dwarf star could no longer resist gravity's pull, no matter how much it compressed its electrons. Oppenheimer and his colleagues extended this reasoning and showed that such a collapse could continue indefinitely, forming what we would later call a black hole. Yet even then, the term black hole did not exist, and the concept was met with disbelief. To many scientists, it sounded like science fiction rather than physics. The Second World War and the decades of nuclear research that followed shifted scientific attention away from these theoretical extremes. It was only in the 1960s, amid the rise of radio astronomy and the discovery of quasars' distant hyperluminous sources powered by compact objects, that the black hole returned from the margins to the centre of astrophysical thought. Physicist John Wheeler coined the term black hole in 1967, giving a name to what had once been unspeakable. From that point forward, the black hole became not a curiosity, but a cornerstone of modern cosmology. The event horizon, the singularity, the notion of space and time ending in darkness, all these became part of the scientific imagination, reinforced by observational evidence and elegant mathematics. Yet beneath the triumph of this narrative, a tension remained. Einstein's equations, flawless on their surface, contained within them the seeds of their own undoing. The singularity at a black hole's core was an infinity, a point where density and curvature became limitless. To most physicists, infinity was a sign of breakdown, not discovery. Still, the success of black hole models in explaining observations was so overwhelming that few dared to question their internal inconsistencies. It is in this historical context that the gravastar idea must be seen, not as a rejection of black holes, but as the latest step in a long tradition of scientific discomfort with infinity. The story of physics has always been one of revision. Newton's mechanics ruled for centuries before Einstein redefined space and time. Einstein's universe, once thought eternal, gave way to Hubble's expanding cosmos. Each era of understanding ends when its equations encounter something they cannot resolve, and in that sense, the gravastar is simply the next attempt to heal a fracture in our understanding. Mazur and Motolo were not iconoclasts seeking to destroy the legacy of relativity. They were heirs to its restless spirit, continuing the same skepticism that Einstein himself had once expressed. The notion that the universe might find a way to avoid singularities echoes Einstein's intuition that nature does not indulge in infinities. Ironically, what he once doubted, the black hole, became one of the best-tested predictions of his own theory, and what he once hoped that the cosmos would preserve its continuity may yet be vindicated by the gravastar hypothesis. Science evolves not through certainty, but through tension. Each generation inherits both the triumphs and the doubts of those before it. When astronomers first observed the monstrous black holes at galactic centres, they confirmed Einstein's equations, but also deepened the mystery those equations had created. When quantum physics revealed the restless energy of the vacuum, it offered both a threat and a promise to relativity's smooth geometry, and a promise of unification. The gravastar is one more voice in this ongoing dialogue, a reminder that the universe may never be captured by a single theory, but only approached through successive approximations. If black holes represented the boldness of 20th century physics, the gravastar represents the humility of the 21st, the realization that even our most successful models may be provisional, and that what we call the end may only be a doorway to another level of understanding. Seen in this light, the gravastar theory does not stand apart from history but continues it. It belongs to the same lineage of ideas that began with Michel's dark stars, passed through Einstein's equations, and matured into the modern study of gravitational collapse. It is the next chapter in humanity's attempt to describe the unfathomable, to reconcile the poetry of the cosmos with the rigor of mathematics. Whether it proves correct or not, its existence shows that science remains alive, that curiosity still outweighs complacency, and that even after a century of studying black holes, we have not yet reached the bottom of their mystery. To comprehend what makes a gravastar so extraordinary, one must look within it, not metaphorically, but structurally. Unlike the simplicity of a black hole, which hides everything behind an event horizon, the gravastar reveals a layered and surprisingly elegant internal composition when described by theory. Its anatomy is divided into three fundamental regions: an inner core filled with vacuum energy, a thin middle shell of exotic matter, and an external environment governed by ordinary space-time. These layers work together to produce an object that outwardly mimics a black hole's gravity, but avoids the singularities that plague it. The inner core is the most mysterious component. In the black hole model, this region would be the singularity, where mass collapses to a point of infinite density. In the gravastar, however, the collapse halts before reaching that catastrophic limit. The material inside undergoes a transformation, becoming a region dominated by vacuum energy, the same kind of energy thought to permeate empty space and drive the acceleration of the universe's expansion. This vacuum energy has negative pressure, meaning that instead of pulling inward like gravity, it pushes outward, acting as a repulsive force. The result is an internal zone that resists further compression, balancing the inward gravitational pull of the outer layers. Physicists describe this region mathematically as having an equation of state, in which pressure equals negative energy density, a condition that creates a stable, self-supporting bubble within the star's remains. Surrounding this core is a shell of exotic matter, an ultra-thin but immensely dense layer that separates the inner vacuum from the outer universe. This shell is perhaps the most critical part of the structure, for it provides the tension needed to maintain equilibrium. The exotic matter composing it is unlike any substance known in ordinary physics. It might consist of particles that violate standard energy conditions, exhibiting negative pressure, or unusual quantum behaviors that allow them to resist collapse. The shell acts as both a boundary and a stabilizer, ensuring that the outward push of the vacuum energy does not blow the object apart, while also preventing the gravitational field from forming a true event horizon. To an external observer, this surface lies infinitesimally close to where the horizon of a black hole would be, so close that distinguishing between the two requires extraordinary precision. This proximity explains why gravastars, if they exist, would appear almost identical to black holes in every measurable way. Beyond the shell lies the outer region, which follows the familiar Schwarzschild solution of Einstein's equations, the same mathematical description that applies to empty space surrounding any spherical mass. In this outer domain, gravity behaves exactly as expected, curving light and dictating the orbits of nearby stars just as a black hole would. There is no visible sign that something unconventional lies beneath. Only when one ventures inward, conceptually if not physically, does the radical difference emerge. The gravastar is thus a delicate balance between competing forces: gravity pulling inward, vacuum pressure pushing outward, and the shell mediating between them. It is a kind of cosmic architecture, built not from matter as we know it, but from the geometry of space itself. In this sense, it resembles a natural fusion of general relativity and quantum theory, combining the curvature of space-time with the quantum properties of vacuum energy. The structure is simple enough to describe mathematically, yet rich enough to inspire endless speculation about its implications. One fascinating aspect of the gravastar's design is its resemblance to phase transitions in condensed matter physics. Just as water can exist in liquid, solid, or vapor states depending on pressure and temperature, the gravastar can be thought of as a phase transition of space-time itself. Inside the core, the geometry behaves like a de Sitter universe. one dominated by vacuum energy and exponential expansion, while outside it behaves like a Schwarzschild space, the vacuum geometry around a compact mass. The thin shell between them serves as the boundary where these two phases of spacetime meet. The comparison to a bubble in a fluid is apt. The gravastar's core expands slightly against the containment of the shell, just as a bubble's interior pressure resists the external pressure of the surrounding liquid. This analogy helps make sense of how such an extreme object could maintain stability over astronomical timescales. The shell's thickness, though small, is crucial. It must be precisely tuned to balance the forces on both sides. Too thin, and the vacuum energy would burst outward. Too thick, and gravity would overwhelm it. The result, if balanced perfectly, is a structure of near-perfect equilibrium. Some models even suggest that the shell could oscillate slightly, vibrating like the surface of a drum under the influence of gravitational waves. These vibrations might produce faint echoes detectable by future observatories, offering one possible way to distinguish gravastars from true black holes. The elegance of this structure lies in its simplicity and symmetry. It fulfills Einstein's equations without resorting to infinities, and it satisfies quantum constraints by incorporating vacuum energy as a natural stabilizing factor. In doing so, it presents a portrait of the universe that seems almost self-correcting, as if the laws of physics refuse to allow absolute destruction. The gravastar becomes not just an astrophysical object, but a philosophical statement, that even in the collapse of stars the cosmos preserves continuity. The idea that such a structure could exist invites us to rethink what it means for something to end. A black hole represents finality, the erasure of form and history. A gravastar, by contrast, represents persistence, a transformation rather than an annihilation. It suggests that even at the edge of collapse, the universe maintains its integrity, building balance from chaos, structure from collapse, and perhaps even meaning from mystery. To grasp the essence of the gravastar's core, one must first understand the nature of vacuum energy, a concept that defies everyday intuition and stands at the frontier of both quantum physics and cosmology. The term vacuum evokes emptiness, a complete absence of matter or energy, but in modern physics this idea is profoundly misleading. What we once imagined as nothingness is, in fact, a restless ocean of activity. Quantum field theory reveals that even in the absence of particles, space itself is alive with fluctuations, tiny, spontaneous surges of energy that continuously create and annihilate virtual particles. These quantum tremors occur everywhere, all the time, forming the unseen background from which the physical universe arises. This invisible energy is what physicists call the vacuum energy, and it is anything but empty. At the quantum level, uncertainty is an inescapable rule. The famous Heisenberg uncertainty principle dictates that certain properties such as position and momentum, or energy and time, cannot both be precisely known. As a result, even empty space cannot remain perfectly still. It must fluctuate. Virtual particles constantly appear and vanish in unimaginably brief intervals, borrowing energy from the vacuum before returning it almost instantly. Though these events are fleeting, their effects are real. They subtly shift the energy levels of atoms, bend light in strong gravitational fields, and even influence the large-scale behavior of the cosmos. Vacuum energy, in short, is the baseline hum of existence, the lowest possible energy state of the universe. In cosmology, it is often associated with the mysterious phenomenon known as dark energy, the force that drives the accelerating expansion of space itself. Observations of distant supernova, cosmic microwave background radiation, and galactic distributions all suggest that roughly 70% of the universe's total energy is locked in this unseen form. Though we cannot touch it or see it directly, its fingerprints are everywhere, shaping the fate of the cosmos. The idea that such energy could also exist inside a collapsed star is one of the boldest aspects of the gravastar hypothesis. Within the extreme environment of gravitational collapse, densities and pressures reach levels that blur the line between matter and space. Under these conditions, quantum effects can no longer be ignored. Mazur and Mottola proposed that when the collapsing matter of a massive star is compressed beyond nuclear density, it could trigger a phase transition in which ordinary particles dissolve into pure vacuum energy. Instead of continuing to collapse toward a singularity, the interior of the star becomes filled with this repulsive energy field. The The vacuum then acts as a counterforce to gravity, halting further contraction and creating a stable, self-sustained bubble. The pressure inside is negative, which means it pushes outward rather than pulling inward. This property is the key to understanding why the gravastar does not implode or explode, but remains balanced at the edge of possibility. In a sense, the vacuum core of a gravastar is like a miniature universe of its own. It behaves as though it were an expanding cosmos trapped within a finite shell, mirroring on a smaller scale what dark energy is doing across the vastness of the real universe. The geometry inside is similar to that of a de Sitter space, a model of a universe dominated by vacuum energy and characterized by constant expansion. Meanwhile, the space outside the shell follows the Schwarzschild geometry of a static gravitational field. The interface between these two regions forms the defining structure of the gravastar. This connection between the quantum and the cosmic is part of what makes the concept so appealing. It suggests that the same fundamental energy shaping the universe at large could also shape its most compact and mysterious objects. The link between vacuum energy, dark energy, and gravastars reveals an unexpected unity across vastly different scales. The universe, it seems, uses the same tool-repulsive pressure to keep itself stable both in the infinite and in the infinitesimal. Yet this elegant symmetry also deepens the mystery. Despite its central role in modern physics, vacuum energy remains one of the least understood aspects of reality. The predicted energy density from quantum field calculations exceeds the observed value by an almost incomprehensible factor, some 120 orders of magnitude. This mismatch, known as the cosmological constant problem, is perhaps the largest discrepancy in all of science. How the universe manages to regulate this energy so precisely is unknown. The gravastar, in its way, offers a kind of natural laboratory for exploring this puzzle. If such objects exist, they would provide direct evidence of how vacuum energy behaves under the most extreme conditions, revealing whether it can indeed act as a stabilizing agent. Understanding this might not only illuminate the fate of collapsing stars, but also shed light on the expansion of the universe itself. In philosophical terms, vacuum energy challenges our very notion of nothingness. It tells us that emptiness is an illusion, that what we call nothing is a seething quantum storm. Even when stripped of matter, radiation and form, the universe remains dynamic. The vacuum is not the absence of being, but the foundation of it, a sea of potentiality from which everything arises and to which everything eventually returns. Within the gravastar, this principle finds its most dramatic expression. What would otherwise be a singularity, a place where physics ends, becomes instead a chamber of infinite potential, a space alive with energy that never dies. The gravastar thus transforms the ultimate void into the ultimate fullness, turning the idea of nothing into something profoundly alive. While the vacuum core of a gravastar provides the expansive energy that resists collapse, the true balance of this extraordinary object depends on the mysterious material forming its outer shell, a layer so strange that it defies nearly every known law of conventional matter. This boundary region, often referred to as the shell of exotic matter, is what keeps the object stable, separating the repulsive vacuum energy inside from the gravitational field outside. Without it, the gravastar would either implode under its own gravity or explode outward like a runaway bubble of space-time. The nature of this shell remains one of the most intriguing and elusive aspects of the gravastar hypothesis. In ordinary physics, matter resists compression due to internal pressure that pushes outward. But as the density increases, even the strongest nuclear forces can no longer hold back gravity's pull. Exotic matter, however, behaves differently. Instead of exerting positive pressure, it produces negative pressure or tension. This means that when gravity tries to squeeze it, the material pushes back not by resisting compression in the usual sense, but by generating an outward pull that counters gravity's inward drag. This unusual behavior allows the shell to act as a kind of cosmic suspension membrane, holding the vacuum core in check while preventing the entire structure from tearing itself apart. The idea of matter with negative pressure might sound like fantasy, but it already exists within modern physics, at least theoretically. The concept emerges naturally in general relativity when describing certain energy conditions, and has been invoked to explain phenomena such as cosmic inflation and dark energy. In those contexts, negative pressure causes space itself to expand. Within the gravastar, it serves a more localized role, stabilizing the region between the expanding vacuum core and the gravitational exterior. The shell acts like a tensioned skin, much like the surface of a soap bubble, except instead of air and water, it separates two different phases of space-time. The physics governing this exotic layer are subtle and complex. The matter composing it may violate what are called the energy conditions of relativity mathematical inequalities that, under normal circumstances, forbid negative energy density or pressure. Violating these conditions doesn't mean breaking the laws of physics. Rather, it suggests that the laws may operate differently in extreme environments. Quantum field theory already predicts scenarios where energy can briefly become negative due to vacuum fluctuations. The famous Casimir effect, for instance, shows that placing two metal plates extremely close together can produce a region of negative energy density between them. If such phenomena can occur in the lab on a microscopic scale, it is not unthinkable that similar principles could operate on cosmic scales under extraordinary gravitational stress. The shell of a gravastar could therefore represent a natural manifestation of these quantum effects amplified by the star's collapse. In this view, exotic matter is not some alien substance, but a particular state of energy that emerges when space-time itself reaches a critical threshold. The properties of this shell also determine how the gravastar interacts with the outside universe. If the surface is perfectly reflective, light and radiation striking it would bounce back, making the object appear nearly indistinguishable from a black hole, whose event horizon lets no light escape. If, however, the shell absorbs some of this radiation or re-emits it over time, subtle observational differences could appear. For example, certain models predict that gravitational waves produced during the merging of two gravastars would exhibit faint echoes as the waves reflect between the shell and the surrounding space-time. Detecting such signals would be one way to test whether these exotic objects truly exist. From a thermodynamic perspective, the shell is also responsible for the gravastar's temperature and entropy. In black holes, these quantities are defined by the area of the event horizon, leading to the famous Hawking radiation and the puzzling relationship between surface area and entropy. For gravastars, the shell takes on that role. It acts as a boundary where quantum processes can occur, potentially radiating heat and maintaining a balance between the cold vacuum inside and the energetic environment outside. This reinterpretation eliminates the paradox of an information-erasing horizon. Information could instead be stored or re-emitted through the complex dynamics of the shell. The very existence of such matter challenges our assumptions about what is physically possible. If negative pressure materials can exist stably, even under extreme conditions, they could have implications far beyond astrophysics, perhaps even for speculative technologies like warp drives or wormholes, which also require exotic matter to function. While such ideas remain far from practical realization, they illustrate how deeply the gravastar concept reaches into the core of physical theory. It asks whether space and matter are truly distinct or whether, at the highest energies, they merge into a single continuum capable of bending and flexing in unexpected ways. In the grand architecture of a gravastar, the shell is more than just a dividing line. It is a frontier where the universe negotiates between opposites, between attraction and repulsion, matter and vacuum, finiteness and infinity. It demonstrates that balance can arise not from uniformity, but from contrast. Gravity tries to pull everything inward, vacuum energy pushes outward, and exotic matter holds the peace between them, an invisible mediator ensuring that cosmic collapse becomes cosmic equilibrium. In this sense, the gravastar is less a static object and more a living system, a dialogue between opposing forces written into the language of geometry. Its shell, though impossibly thin, represents one of nature's most remarkable achievements: the ability to transform chaos into stability by using the strangest ingredients in the universe. How could a gravastar actually form in nature? This question sits at the center of the debate, for even the most elegant theory must eventually meet the test of cosmic reality. The birth of a gravastar would begin in the same way as the birth of a black hole, with the death of a massive star. When a star many times heavier than the Sun runs out of nuclear fuel, it can no longer sustain the outward pressure that counteracts gravity. The stellar core collapses under its own weight, crushing atoms and fusing protons with electrons to form neutrons. The outer layers explode outward in a supernova, leaving behind a dense remnant a neutron star if the mass is moderate. or, according to standard theory, a black hole if the mass exceeds a certain threshold. In the gravastar scenario, the story diverges at the moment when collapse should become unstoppable. As the star shrinks beyond nuclear density, conventional matter begins to lose its familiar structure. The equations of general relativity predict that nothing can halt the implosion, but at these unimaginable densities, quantum effects can no longer be ignored. Mazur and Mottola proposed that instead of continuing to compress indefinitely, the collapsing matter could undergo a phase transition, turning into vacuum energy. This transformation would be abrupt but decisive. The intense gravitational field would trigger a shift in the very state of space-time, converting the collapsing core into a region dominated by negative pressure. Once this transition begins, the repulsive force of the vacuum energy counteracts gravity's pull, slowing the collapse and eventually halting it altogether. The result is a core that no longer behaves like ordinary matter, but like an expanding patch of vacuum, pressing outward against the infalling material. At the same time, a thin shell of exotic matter forms at the boundary where the outward-pushing vacuum meets the inward-pulling gravity of the remaining mass. This shell stabilizes the system, sealing the vacuum inside and preventing further collapse. The star, which seemed destined to vanish into a black hole, instead settles into a new equilibrium state, a gravastar. In this way, the formation of a gravastar resembles a kind of cosmic self-correction. Nature refuses to allow infinity, and instead of permitting space-time to tear itself apart, it reorganizes the collapsing star into a structure that preserves balance. Whether this process occurs naturally remains uncertain, but it fits comfortably within the laws of physics as we know them, provided quantum effects become dominant at extreme densities. One of the appealing aspects of this scenario is that it requires no exotic initial conditions or alien interventions. Any sufficiently massive star could, in principle, end its life this way if the right thresholds are met. The challenge is understanding exactly when and how this quantum phase transition would occur. Some theorists have speculated that it might depend on factors such as rotation, magnetic fields, or the rate of collapse. Others suggest that quantum gravity effects could trigger the transition spontaneously when curvature reaches a critical limit, just as water spontaneously boils once it reaches its boiling point. In such a view, the boundary between black hole formation and gravastar formation could be razor-thin, perhaps determined by minute variations in the conditions at the moment of collapse. Two stars of identical mass might meet entirely different fates, one becoming a black hole, the other a gravastar, depending on subtle quantum fluctuations at the brink of singularity formation. This unpredictability makes the phenomenon even more intriguing. It implies that the universe could be filled with both kinds of objects, indistinguishable from afar but fundamentally different within. The formation process would also be unimaginably fast. Once the vacuum transition begins, it would cascade through the collapsing core in fractions of a second, releasing intense bursts of energy. Some scientists have proposed that this process could produce unique signatures, brief flashes of radiation, or distinctive gravitational wave patterns that might one day be detectable. In particular, the birth of a gravastar might leave behind a ringing effect as the new structure oscillates before settling into equilibrium. Detecting such echoes could provide the first direct evidence that these exotic stars are real. Another open question concerns the ultimate stability of gravastars. Once formed, could they persist for billions of years like black holes, or would they slowly evolve, perhaps leaking energy through quantum processes? Some models predict that gravastars could be almost perfectly stable, while others suggest that their shells might gradually thin or dissipate, allowing the vacuum inside to expand. If that were true, a gravastar might eventually evaporate in a manner very different from a black hole, leaving behind a faint burst of radiation or a shell of exotic particles. The long-term fate of such objects remains one of the greatest mysteries in the theory. Despite these uncertainties, the formation hypothesis offers something rare in theoretical astrophysics, a plausible mechanism for avoiding infinities without violating known laws. It shows how quantum principles could intervene in gravity's most extreme domain, transforming collapse into structure. It also echoes a recurring theme in nature, the emergence of stability from instability. Just as atoms resist collapse through quantum pressure and stars balance gravity with fusion, so might the universe resist singularity through the quantum properties of the vacuum itself. The gravastar, in this sense, is an expression of nature's tendency towards self-regulation. If such objects truly exist, they would stand as proof that even death in the cosmos is not final, but transformative. Stars would not end in absolute darkness, but in a new state of equilibrium, preserved by the same laws that once seemed to doom them. If gravastars truly exist, the greatest difficulty in proving their reality lies in the fact that they look almost exactly like black holes from the outside. Their gravitational fields, light-bending properties, and overall behavior are nearly indistinguishable to even our most advanced instruments. Both types of objects can form accretion disks of hot gas spiraling around them. Both emit powerful X-rays and jets as matter falls inward, and both warp the fabric of space-time so strongly that light itself curves around them. From a distance, a gravastar and a black hole would appear as the same dark void framed by glowing plasma. This near-perfect disguise poses one of the most formidable observational challenges in modern astrophysics. In essence, the gravastar is a black hole impersonator, a cosmic mimic whose differences hide behind the limits of measurement. The key distinction lies just beyond what we can currently see. A black hole's defining feature is its event horizon, the invisible boundary from which nothing can escape. A gravastar, by contrast, has a physical surface, though one so close to the Schwarzschild radius that it might as well be hidden behind an optical illusion. For a distant observer, any light emitted from that surface would be so strongly redshifted by gravity that it would lose nearly all its energy, making it effectively invisible. This gravitational redshift ensures that even if the gravastar emits a faint glow, it would be drowned out by surrounding radiation. The difference between a true event horizon and an ultra-redshifted surface is therefore almost impossible to detect directly. Modern telescopes, even the most powerful ones like the Event Horizon telescope that captured the first image of a black hole's shadow, cannot resolve details at such extreme scales. They show us silhouettes, not interiors. The image of the supermassive black hole in the galaxy M87, for example, could just as easily be the shadow of a gravastar. The data alone cannot yet tell us the difference. Observationally, both objects create the same ring of light photons trapped in orbit, near the critical radius where gravity bends them into near-circular paths. The only subtle distinction might lie in how that light fluctuates over time. If a gravastar possesses a reflective surface instead of an absorbing horizon, some of the radiation and particles falling toward it might bounce back, producing delayed echoes in the emitted signals. These echoes would be incredibly faint and fleeting, requiring instruments of extraordinary sensitivity to detect. Gravitational wave observatories like LIGO and Virgo have already begun searching for such signatures in the ripples of space-time produced by merging compact objects. When two massive remnants collide, the resulting gravitational waves carry a detailed imprint of the object's internal structure. In a black hole merger, the waves ring down smoothly as the new black hole settles into equilibrium. In a gravastar merger, however, the waves might exhibit secondary pulses, echoes reverberating between the shell and the surrounding space-time. Detecting such patterns would be a revolutionary discovery, a sign that the event horizon may not be the absolute boundary we once thought it was. Yet even this test is fraught with difficulty. Gravitational wave data is noisy, and the differences between models can be subtle. For every potential hint of an echo, skeptics can point to alternative explanations, instrumental artifacts, statistical coincidences, or noise misinterpreted as signal. The search continues, with new detectors being developed to increase sensitivity and resolution. Future observatories, such as the planned space-based ELISA mission, may one day have the precision needed to reveal the telltale fingerprints of gravastars. Another challenge comes from thermal radiation. A true black hole emits Hawking radiation faint, theoretical heat caused by quantum effects near the horizon. In practice, this radiation is far too weak to be detected for any realistic black hole. A gravastar, by contrast, might emit radiation from its surface depending on the properties of its shell. However, because of extreme redshift, this radiation would be almost entirely invisible at observable wavelengths. Distinguishing between the two would require precise spectral measurements of the accretion disks or jets surrounding these objects, measurements that push the boundaries of current technology. Even then, the interpretations would remain uncertain. Every observable difference between a black hole and a gravastar hides beneath layers of complexity, distortion, and uncertainty. We are in effect staring at shadows and trying to deduce the nature of the object that casts them. The difficulty is compounded by distance. Most of the candidates for black holes lie thousands or even millions of light years away. Light from these regions is distorted by interstellar dust, gravitational lensing, and relativistic effects, erasing the fine details that might reveal a gravastar's true nature. And yet, it is precisely these challenges that make the search so compelling. The possibility that some of the black holes we have already observed are in fact gravastars adds a layer of mystery to every detection. Each new image, each gravitational wave event, each spectral anomaly could hold a clue. The boundaries of observation are not static. They expand with every generation of instruments, algorithms, and imagination. The gravastar, elusive as it may be, serves as a reminder that what we call evidence is always filtered through the lens of our tools and theories. We see only what our instruments allow, and beyond that lies an uncharted domain of speculation and potential. The challenge of distinguishing a gravastar from a black hole is not merely technical, it is philosophical. It forces us to confront the limits of perception itself. Perhaps, as technology improves, the universe will reveal which of these two cosmic fates collapse into oblivion or transformation into equilibrium it truly favours. Until then, every dark shadow against the stars remains an open question, a silent possibility waiting to be understood. When the first gravitational waves were detected in 2015 by the LIGO Observatory, it marked one of the most transformative moments in modern astrophysics. For the first time, humanity could not only see the universe through light, but also hear it through the vibrations of space-time itself. The ripples that passed through Earth came from the collision of two black holes more than 1 billion light-years away, confirming a prediction made by Einstein a century earlier. But beyond confirming relativity, those waves also opened a new path to probe the very heart of compact objects, their internal structure, their behaviour during mergers, and perhaps their true identity. For researchers exploring the possibility of gravastars, gravitational waves became a kind of Rosetta Stone, a message from the cosmos that might reveal whether black holes are really what we think they are. When two massive bodies spiral toward each other, their mutual gravity distorts the surrounding space-time, creating oscillations that spread outward at the speed of light. The pattern of these waves, how their frequency and amplitude change over time, depends entirely on the nature of the merging objects. In a black hole merger, the final stage produces a distinct ring-down, as the newly formed black hole settles into a stable state. This phase is smooth and predictable, described with exquisite accuracy by Einstein's equations. But if the colliding objects are gravastars rather than true black holes, the story could unfold differently. Because gravastars lack event horizons and have reflective surfaces, part of the energy released during the merger might bounce between the inner shell and the surrounding space-time before escaping. This would produce secondary oscillations known as echoes, arriving milliseconds or seconds after the main signal. These echoes are the signature that scientists have been searching for, a possible fingerprint of the gravastar's existence. Detecting them, however, is far from straightforward. Gravitational wave detectors measure distortions smaller than a fraction of the width of a proton, and the signals they capture are buried in noise from the Earth itself. Vibrations, temperature fluctuations, even quantum uncertainty in the lasers. Distinguishing an echo from background noise requires meticulous analysis and sophisticated algorithms. Some studies have reported tentative hints of such echoes in the data from LIGO and Virgo, while others have found no statistically significant evidence. The debate continues, highlighting both the promise and the challenge of exploring this new frontier. Even if echoes exist, their characteristics depend heavily on the properties of the gravastar. The thickness and reflectivity of its shell, the density of its vacuum core, and the speed at which gravitational waves propagate through its interior. Small changes in these parameters could drastically alter the echo pattern, making predictions complex and uncertain. Theorists have developed models simulating how different gravastar configurations would behave during a merger. Some predict sharp, regular echoes spaced at fixed intervals, while others suggest more chaotic patterns fading over time. Each variation paints a slightly different picture of how space-time might respond to the absence of an event horizon. What makes these investigations so important is that gravitational waves carry direct information about the geometry of space-time itself. Unlike light, which can be absorbed or scattered, gravitational waves travel through matter almost unimpeded. They are the perfect messengers for probing regions otherwise hidden from view. In principle, they can reveal whether the inner structure of a compact object terminates in an absolute horizon or continues into something more complex, like the surface of a gravastar. The LIGO-Virgo-Cagra collaboration, along with planned observatories such as LISA in space and the Einstein telescope on Earth, are steadily improving the sensitivity of their instruments. Future generations of detectors may be able to resolve these subtle echoes with far greater clarity. If confirmed, they would provide the first direct evidence that event horizons are not the final boundary of the universe, but only a threshold we have misunderstood. Even now, the mere search for such clues has reshaped theoretical physics. It has forced scientists to reconsider how energy and information move during extreme gravitational events. In the conventional picture, once two black holes merge, all details of their past vanish behind a single horizon, leaving behind only mass, charge, and spin. But if gravastars exist, the merger could retain a kind of memory. The vibrations of the resulting object might encode information about its formation, about the structure of the shell and the dynamics of the vacuum within. Such an outcome would have profound implications for the study of quantum gravity and the conservation of information in the cosmos. Gravitational waves, in this sense, have become more than a new observational tool, they are a new language. Each chirp recorded by a detector is a sentence written in the grammar of space-time, carrying information from realms no light can reach. We are only beginning to learn how to read this language. The detection of echoes or any deviation from standard black hole predictions would not only confirm the existence of gravastars, but also challenge our deepest assumptions about gravity itself. It would suggest that space-time is not an all-consuming abyss, but a dynamic fabric capable of storing and releasing information in ways we are only beginning to imagine. For now, the evidence remains inconclusive, and skepticism remains a healthy part of the process. But the search continues, and with every new merger detected, we listen more closely to the universe's whispers, hoping that somewhere amid the noise, a faint echo might finally answer the question that has haunted physics for decades. What really lies beyond the darkness we call a black hole? The concept of the gravastar, though born from the intersection of relativity and quantum mechanics, extends far beyond a single class of astrophysical object. If such entities truly exist, they would have profound consequences for our understanding of the universe itself, challenging the very foundations of cosmology, information theory, and the nature of reality. Their implications reach from the microscopic laws governing quantum fields to the grand structure of the cosmos. At the most immediate level, gravastars offer a potential solution to the most troubling paradoxes of black hole physics. The traditional picture of a black hole involves a singularity, a point of infinite density where all known laws break down. For decades, physicists have wrestled with how information behaves in the presence of such a singularity. According to quantum mechanics, information about physical systems can never be destroyed, yet black holes appear to erase everything that falls into them. This tension between relativity and quantum theory produced the famous information paradox, one of the greatest unsolved problems in physics. The gravastar elegantly sidesteps it. Because it possesses no singularity and no true event horizon, information need not vanish from the universe. It may instead be preserved in the complex structure of the shell or reflected outward in subtle ways. This perspective restores the continuity of physical law and suggests that the universe remains coherent even in its most extreme moments. Beyond this, gravastars could reshape our view of cosmic evolution. If they exist in large numbers, they might play a role in shaping galaxies and influencing the distribution of matter in the universe. Black holes are thought to anchor galactic centers, regulating star formation through the release of energy from accreting matter. Gravastars, with their internal reservoirs of vacuum energy, might behave differently. Instead of swallowing all that approaches, they could interact with surrounding matter in ways that subtly modify the galactic environment. Some researchers have speculated that the presence of gravastars might even contribute to dark matter, or dark energy phenomena on cosmic scales, adding an entirely new layer to the puzzle of the universe's composition. The link between gravastars and dark energy is especially compelling. Both rely on the strange properties of vacuum energy, negative pressure, repulsion, and a constant density independent of expansion. If the vacuum core of a gravastar represents a localized concentration of the same energy driving cosmic acceleration, then the universe itself might be thought of as a vast gravastar, with galaxies and clusters embedded within its shell. This analogy may be poetic, but it captures a deep symmetry. The smallest and largest structures in the cosmos could be governed by the same underlying principle. The gravastar thus becomes a microcosm of the universe, reflecting its geometry and its hidden energies. Philosophically, this interpretation is profound. It suggests that the boundaries between inside and outside, between matter and vacuum, between life and death of stars, are not absolute but continuous. What we call destruction may simply be transformation on a different scale. The gravastar replaces the image of cosmic collapse with one of cosmic renewal, a process in which gravity and quantum effects conspire not to annihilate but to reorganize. Such a perspective aligns with a recurring theme in nature, the avoidance of infinities. From atoms to galaxies, stability arises when competing forces reach equilibrium. The gravastar is the ultimate expression of this principle, a structure where the universe finds balance at the edge of its own extremes. If this idea proves correct, it would also have implications for the ultimate fate of the cosmos. Some cosmological models predict that the universe may one day collapse back on itself, forming a singular big crunch. Others foresee endless expansion. A gravastar-like mechanism could offer a third path, a self-regulating process where expansion and contraction coexist in balance. Just as a dying star avoids total collapse by converting to a gravastar, perhaps the universe itself could undergo a similar transition, transforming into a stable configuration rather than collapsing or dissipating entirely. This analogy blurs the boundary between cosmology and astrophysics, between the destiny of stars and the destiny of everything. The philosophical ripples extend even further. If the gravastar replaces the black hole, then our perception of cosmic death must change. For centuries, black holes have represented the ultimate void, the erasure of form and meaning. They stood as metaphors for oblivion, consuming everything, revealing nothing. The gravastar, by contrast, embodies preservation and transformation. It turns the symbol of annihilation into one of continuity. Instead of being a tomb of the universe, it becomes its chrysalis. This shift in imagery may seem poetic, but it influences how science approaches the unknown. It encourages us to seek continuity where we once expected endings, to look for structure where we assumed chaos. In practical terms, this means re-examining the assumptions that underlie cosmological models, from the behavior of dark energy to the formation of structure in the early universe. If gravastars truly exist, they could serve as natural laboratories for testing theories of quantum gravity, the elusive framework that seeks to unify Einstein's relativity with quantum mechanics. The conditions inside their shell's immense curvature, vacuum energy dominance, and quantum effects on a macroscopic scale could mirror those present during the first moments after the Big Bang. Understanding them could therefore unlock the secrets of the universe's birth. The cosmic implications of gravastars are both humbling and exhilarating. They remind us that our theories are provisional, that every apparent limit may conceal a deeper order. They invite us to see the cosmos not as a collection of separate events, but as a continuous fabric of transformation, where collapse becomes creation and darkness hides an unseen light. In the grand scheme, the gravastar may be more than just an alternative to black holes. It may be a clue to the deeper unity of existence itself, a whisper from the universe telling us that even in the places we call void, there is always something still alive. The search for a bridge between quantum mechanics and general relativity, the two great pillars of modern physics, has long been one of humanity's most ambitious intellectual quests. On one side lies the world of the very small, governed by uncertainty, probability, and discrete interactions. On the other stands the world of the very large, where space and time curve smoothly under the weight of matter and energy. For more than a century, physicists have tried to reconcile these two realities, yet a complete theory of quantum gravity remains elusive. The gravastar, though not intended as a full unification, stands at the crossroads of these frameworks. It may not solve the riddle of quantum gravity outright, but it provides a potential stage on which the two theories might finally meet. In a sense, it acts as a natural testing ground for ideas that otherwise remain abstract. Black holes have always posed a problem for unification because their singularities represent the breakdown of both theories at once. Inside the event horizon, gravity becomes infinite, and quantum mechanics ceases to make sense. The gravastar replaces that singularity with a finite structure where quantum and relativistic effects coexist. Its vacuum core, filled with energy density and negative pressure, behaves according to quantum principles, while its exterior obeys Einstein's equations of curvature. The shell that divides them becomes a literal boundary between the quantum and the classical surface, where two incompatible descriptions of nature must somehow agree. This makes the gravastar a kind of a laboratory for quantum gravity in the cosmos. The most compelling feature of this boundary is that it functions like a phase interface, much like the surface between liquid water and ice. Within the inner vacuum, quantum fields dominate, while outside, classical spacetime prevails. The physics at the shell's surface could therefore reveal how the smooth geometry of general relativity emerges from the jittery fluctuations of quantum fields. If the gravastar truly exists, it would embody the transition between these two regimes, providing a glimpse into the fabric of reality at its most fundamental level. Some researchers have drawn parallels between gravastars and certain ideas in loop quantum gravity, a theory that attempts to quantize spacetime itself by describing it as a network of discrete loops. In this framework, singularities are naturally avoided because space cannot be compressed below a minimum volume. Similarly, string theory. The other major contender for quantum gravity predicts that the universe's fundamental constituents are tiny vibrating strings, whose tension and interactions prevent infinite densities. Both approaches suggest that nature resists infinities through structure, not through absence. The gravastar, with its stable core and self-balancing shell, reflects this same principle. It shows how the collapse of matter might be halted by the quantum properties of space itself. Another intriguing connection arises in the study of entanglement entropy and holography. In recent decades, physicists have discovered that gravity and quantum information may be deeply intertwined. The holographic principle, for instance, proposes that all the information contained in a volume of space can be described by data encoded on its boundary, much like a hologram. In black hole physics, this idea manifests through the Bekenstein-Hawking entropy, which links the surface area of the event horizon to the amount of information it holds. Gravastars, with their tangible shells, offer a more physical realization of this concept. Their boundaries could literally store and process information about the energy and matter within, creating a bridge between holographic theory and observable structure. This turns the gravastar from a mere astrophysical curiosity into a potential cornerstone of information physics. If black holes are paradoxical in their information loss, gravastars could represent nature's resolution, a system where information is preserved at the interface between quantum and classical realms. The shell would then act not only as a structural boundary, but as a computational one, encoding the data of everything that falls into it. This perspective aligns with recent ideas in quantum gravity that view space-time as emergent, not fundamental. According to this view, geometry arises from the entanglement patterns of quantum fields. The more entangled the fields, the smoother the geometry becomes. A gravastar could then be seen as a kind of cosmic condensate of entanglement, where geometry and information intertwine. The vacuum core represents the quantum potential, the shell the interface of entanglement, and the exterior the emergent classical spacetime. In this sense, the gravastar may be not just an astronomical object, but a prototype for how reality itself is organized. The implications extend to the earliest moments of the universe. During the Planck epoch, when the cosmos was unimaginably dense and hot, the same tension between gravity and quantum mechanics must have governed its behavior. If the gravastar mechanism truly reflects nature's way of avoiding singularities, it could apply not only to collapsing stars but also to the birth of the universe itself. The Big Bang might not have been an explosion from a singular point, but a transition similar to the formation of a gravastar's vacuum core, a quantum phase change in which spacetime emerged from a pre-geometric state. The parallels are striking. Both involve extreme curvature, vacuum energy, and the conversion of collapse or compression into expansion. Thus, the study of gravastars may reveal not only how stars die, but how the universe came to life. Quantum gravity, for all its complexity, seeks precisely this kind of bridge, a way to connect the smoothness of the cosmos to the granularity of the quantum world. The gravastar does not claim to provide the final theory, but it may show us where to look. By replacing the mathematical infinity of a singularity with the physical reality of structure, it hints that the universe's deepest mysteries may not lie beyond our reach, but hidden within its most balanced forms. Beyond equations and theories, the idea of the gravastar touches something profoundly philosophical. It challenges not only how we describe the universe, but how we understand existence itself. For centuries, black holes have stood as symbols of finality, the cosmic equivalents of death and oblivion. They represent the ultimate endpoint of matter and energy, where everything collapses into an unknowable void. To many thinkers, they even mirrored the limits of human knowledge, a point beyond which thought could not venture. The gravastar overturns that symbolism. Instead of annihilation, it suggests transformation. Instead of an ending, it offers continuation. In doing so, it reframes how we think about the universe, replacing despair with balance, destruction with metamorphosis. This shift is more than poetic. It reflects a fundamental change in our philosophical relationship with the cosmos. Throughout history, science and philosophy have often danced together. Each time humanity has faced a concept too vast or too abstract, philosophy has given it meaning while science sought its mechanism. When Newton revealed that gravity bound the heavens and the earth under the same law, it transformed not just physics but metaphysics. The universe became a rational order rather than a divine mystery. When Einstein bent space and time into a single fabric, he redefined causality and the meaning of motion. The gravastar, though newer and more speculative, carries a similar philosophical charge. It asks whether reality is truly discontinuous, whether there can exist genuine boundaries between being and nothingness. The black hole suggests that such boundaries exist. The gravastar suggests the opposite. In this view, nothingness itself is an illusion, a threshold mistaken for an end. What we call void may merely be a different mode of existence, hidden behind the limits of perception. This idea resonates deeply with ancient philosophical traditions. In Eastern metaphysics, emptiness is not non-existence but potentiality, the fertile ground from which all things arise. In Western thought too, thinkers from Spinoza to Whitehead imagined a universe where substance is eternal, endlessly transforming but never vanishing. The gravastar fits within this lineage of continuity. It embodies a cosmos that renews itself, where collapse becomes creation, and opposites coexist in harmony. Its structure, a balance between outward expansion and inward compression, becomes a metaphor for the universe itself, for life and death, for the dance of forces that sustains reality. Even the name gravastar, short for gravitational vacuum star, carries philosophical weight. It implies unity between opposites, gravity, the force of attraction, and vacuum, the expression of emptiness. The combination is paradoxical yet harmonious, symbolizing how tension gives rise to form. The gravastar thus stands as both a physical hypothesis and a philosophical statement about balance. The idea that the universe preserves itself not by avoiding extremes but by reconciling them. From a human perspective, this reinterpretation of cosmic death has psychological implications as well. Black holes, in their starkness, evoke existential dread. They remind us of mortality, of the eventual erasure of all structure and meaning. Gravastars, on the other hand, suggest that even in the face of collapse, order can re-emerge. They embody resilience, the possibility that the universe does not simply consume itself, but continually reorganizes into new forms. This echoes the broader human intuition that destruction is never total, that behind every end lies the seed of renewal. In this sense, the gravastar is not merely a theoretical construct, but an emblem of persistence, a cosmic affirmation that nothing truly disappears. The philosophical significance of gravastars also extends to questions of knowledge and perception. For much of modern science, the event horizon of a black hole represented an epistemological boundary, the line beyond which observation fails. It was the edge of knowability itself. The gravastar softens that boundary. If its surface exists and can, in principle, interact with the outside world, then the ultimate mysteries of collapse are not beyond reach, but simply hidden by scale. Knowledge, in this view, is not forbidden, but deferred. The universe may still hold secrets, but it does not bar us from seeking them. This perspective aligns with a broader shift in scientific philosophy from absolutism to relationalism. In the old paradigm, singularities marked absolute limits, where the laws of nature broke down irreparably. In the new one, such infinities are signs not of failure but of incompleteness, clues pointing toward deeper structure. The gravastar embodies this attitude. It invites humility without surrender, curiosity without despair. It tells us that the unknown is not a void but a frontier, waiting to be understood in new terms. Philosophically, the gravastar also reawakens the ancient question of what it means for something to exist. If the vacuum inside a gravastar is filled with energy, if nothing is actually something, then the very notion of being must be reconsidered. Perhaps existence is not defined by substance but by interaction, not by what something is but by how it behaves within the web of space-time. In that case, the gravastar half vacuum, half matter becomes an allegory for existence itself, dynamic, relational, and self-sustaining. It blurs distinctions between emptiness and fullness, between inside and outside, between presence and absence. Such reflections remind us that science, at its highest level, always circles back to philosophy. Every discovery carries with it a shift in worldview, an invitation to think differently about what reality means. The gravastar, whether ultimately proven or not, fulfills that role. It reminds us that the universe is not a machine running toward entropy, but a living system capable of equilibrium, renewal, and perhaps even purpose. In contemplating gravastars, we're not merely studying the death of stars, we're glimpsing the persistence of order in a universe that refuses to end. The gravastar is far from the only attempt to replace or reinterpret the classical concept of the black hole. Over the past few decades, physicists have proposed a range of alternative models that try to resolve the same inconsistencies between relativity and quantum mechanics. Each offers its own explanation for how the universe might avoid singularities, and each comes with its own advantages and difficulties. Understanding where the gravastar fits among these theories helps clarify not only its uniqueness, but also the broader search for coherence in our picture of cosmic collapse. One of the earliest competing ideas is the boson star, a hypothetical object made not of ordinary atoms or neutrons, but of bosons particles that can occupy the same quantum state without exclusion. Unlike fermions, which resist compression due to the Pauli principle, bosons can merge into a single quantum wave, allowing matter to clump together in unusual ways. A boson star would be transparent, compact, and extraordinarily stable, sustained by quantum pressure from its wave-like nature rather than thermal or nuclear forces. Though they could mimic black holes in mass and compactness, they lack horizons or singularities. The difference is that boson stars are composed entirely of particles, whereas gravastars are built from the geometry of space-time itself, a shell enclosing vacuum energy. Where the boson star is matter-based, the gravastar is structure-based. Another proposal, the dark energy star, bears a much closer resemblance to the gravastar. Developed by George Chaplin and others, this model also relies on vacuum energy to halt gravitational collapse. In a dark energy star, space-time transitions from normal behavior to a phase dominated by dark energy, as matter approaches the threshold of an event horizon. Instead of forming a singularity, the collapsing star converts into a region where repulsive pressure balances gravity. The distinction between dark energy stars and gravastars often lies in the details of how this transition occurs. In the gravastar picture, the shell is sharply defined, a thin boundary separating interior vacuum from exterior space. In dark energy stars, the transition is gradual, extending over a finite region. This subtle difference changes how each would interact with infalling matter and radiation. Both ideas, however, share the same underlying philosophy. Nature avoids infinities by changing phase, turning collapse into equilibrium through the quantum properties of vacuum energy. There are also fuzzballs, a concept emerging from string theory. In this view, what we call a black hole is actually a tangled ball of strings and branes, each representing a distinct microstate. The horizon is not a smooth boundary, but a chaotic surface where quantum structure dominates. Every black hole in this interpretation is unique, determined by the particular arrangement of its microscopic components. Fuzzballs eliminate the singularity and preserve information because the interior structure is rich and varied. The gravastar differs in simplicity. It relies on macroscopic geometry rather than microscopic string configurations. Yet both models share the desire to preserve information and avoid the paradox of disappearance. In a sense, the fuzzball is the quantum mechanical counterpart to the gravastar's geometric elegance. One microscopic, the other macroscopic, both pointing toward a universe that refuses absolute loss. Another speculative class of alternatives is known as firewalls. According to some interpretations of quantum mechanics, if information must be preserved, then the region just outside a black hole's event horizon could not be empty. As relativity predicts, it would be filled with high-energy radiation that destroys anything falling in. The firewall hypothesis solves the information paradox at the cost of breaking the smoothness of space-time. Gravastars, by contrast, achieve the same goal without such violence. They allow information to survive by providing a physical boundary, the shell, rather than a destructive barrier. In that sense, the gravastar restores harmony between relativity and quantum theory, rather than forcing one to surrender. There are even more exotic proposals: Planck stars, quantum black holes, non-singular cores, each trying to describe what happens when gravity meets quantum physics at its limit. Planck stars, for example, arise in loop quantum gravity. They are thought to form when collapsing matter reaches Planck density, where quantum geometry effects generate a repulsive force that halts further collapse. The core then bounces, potentially releasing energy in a burst resembling a gamma-ray flash. Again, the philosophy is the same. Nature avoids infinity through structure. The gravastar fits naturally into this family of ideas, but distinguishes itself through its elegance and minimalism. It does not rely on speculative particles or string dimensions, but on ingredients already present in general relativity and quantum field, theory vacuum energy, negative pressure, and curved space. It takes the familiar language of Einstein's equations and rewrites it to include a quantum correction, creating stability from balance rather than from complexity. Philosophically, this makes it one of the most appealing alternatives, because it feels like an organic extension of known physics rather than an overhaul. Despite the similarities, these competing models often converge in their predictions, which makes experimental distinction extremely difficult. Whether one observes a black hole, a gravastar, a boson star, or a fuzzball, the gravitational field outside looks almost identical. The differences lie hidden deep within, in regions that remain inaccessible to direct observation. This convergence suggests that many of these models may be describing different facets of the same underlying principle, that the universe forbids singularities and ensures information persists through some form of internal structure. The challenge now is not to decide which model is true in isolation, but to uncover what they have in common. The gravastar stands out because it bridges simplicity and depth. It proposes a mechanism that is at once physical and metaphysical, a meeting point between the continuous and the discrete. Whether it turns out to be the final word or just another step toward understanding, its place among alternative theories marks a profound shift in how we think about cosmic extremes, not as breakdowns, but as thresholds where new forms of order begin. For all its elegance, the gravastar remains a hypothesis awaiting empirical confirmation. Its beauty lies in the way it reconciles contradictions between relativity and quantum theory. But the universe does not yield its secrets easily. To transform the gravastar from speculation into established science, researchers must find a way to detect it, an endeavour that pushes the limits of observation and theory alike. The difficulty stems from the gravastar's uncanny resemblance to a black hole. Outwardly, both distort space-time in almost identical ways. Their gravitational fields are described by the same equations, and their shadows, those dark regions surrounded by glowing accretion disks, are practically indistinguishable. Yet hidden beneath that similarity are differences subtle enough to test the very precision of modern astrophysics. Scientists have identified several possible paths toward discovery, each promising but fraught with challenges. The most immediate method involves gravitational waves, those faint tremors in the fabric of space-time caused by violent cosmic events such as mergers of compact objects. As detectors like LIGO and Virgo continue to record these signals, physicists scrutinize the data for minute deviations from the patterns predicted by black hole models. A gravastar, having a physical surface instead of a near-event horizon, would produce echoes or secondary oscillations after the main gravitational wave burst. These echoes, caused by reflections between the shell and surrounding space, would appear as faint ripples following the primary signal. While a few studies have hinted at their presence, none have yet reached statistical certainty. Nevertheless, every new detection improves our ability to listen, refining the cosmic symphony in which such faint notes might one day be heard clearly. Another promising route lies in high-resolution imaging of galactic cores. The Event Horizon Telescope's image of the black hole in M87 demonstrated that we can now capture the shadows of these extreme objects. Future upgrades may go beyond silhouettes to reveal temporal fluctuations or spectral features that betray a surface beneath the apparent void. A gravastar's shell, for example, could reflect or reprocess radiation differently from a true horizon, causing subtle variations in brightness or polarization. Detecting such differences requires instruments of unprecedented sensitivity and stability, perhaps including space-based interferometers that can observe at multiple wavelengths simultaneously. Advances in X-ray and gamma-ray astronomy may also play a key role. The behavior of matter spiraling into compact objects depends on the conditions near their boundaries. If a gravastar possesses a tangible surface, infalling gas might strike it and release bursts of high-energy radiation distinct from the steady glow expected from black holes. These emissions could appear as short, periodic flares or irregular flashes. Identifying them, however, is complicated by the chaotic environments surrounding active galactic nuclei, where competing processes can mask or mimic such signals. Researchers must therefore combine timing, spectral analysis, and polarization studies to isolate the gravastar's unique fingerprints from cosmic noise. The next frontier in this search involves space-based gravitational wave detectors like LISA, Laser Interferometer Space Antenna, scheduled for launch in the 2030s. Orbiting millions of kilometers apart, LISA's sensors will detect lower frequency waves from massive black hole candidates, potentially revealing long-lasting resonances that ground-based detectors cannot perceive. If gravastars populate the centers of galaxies, LISA may capture the subtle breathing of their shells as they interact with infalling matter or merge with other compact objects. Such data could finally determine whether event horizons truly exist or whether nature prefers the gravastar's balance between gravity and vacuum. Yet observation is only half the task. Theoretical progress remains just as essential. Modeling gravastars requires uniting general relativity with quantum field effects, a computational challenge that pushes existing methods to their limits. Physicists are now employing numerical relativity, simulating space-time on supercomputers to explore how vacuum energy and exotic matter might interact under collapse conditions. These simulations help predict observational signatures, guiding astronomers toward what to look for. Meanwhile, developments in quantum gravity, particularly in loop quantum cosmology and holographic theory, continue to provide insights into how space-time behaves near critical densities. Each advance tightens the conceptual framework in which gravastars might fit. Future research may also explore astrophysical consequences if gravastars turn out to be real. For instance, the distribution and mass spectrum of compact objects in the universe might change. Some of the supermassive black holes believed to anchor galaxies could instead be gravastars, their internal pressure influencing the motion of surrounding stars and gas in subtle ways. This possibility has profound implications for models of galaxy formation and evolution. Moreover, if gravastars can store and release information or energy differently than black holes, they might affect cosmic feedback mechanisms, how energy cycles through interstellar space, and regulate starbirth. Even speculative technologies such as harnessing energy from vacuum fluctuations or manipulating gravity through exotic matter could gain theoretical grounding from gravastar research. The pursuit of gravastars is therefore not merely an exercise in curiosity. It is a journey toward understanding how reality organizes itself at its extremes. Each step, whether observational or theoretical, teaches us more about the rules governing the universe. The search unites disciplines once thought separate: astrophysics, quantum mechanics, thermodynamics, and philosophy into a single narrative of exploration. Whether or not gravastars are ever confirmed, the effort to find them is already reshaping how we study the cosmos. It forces us to refine our tools, expand our imagination, and question assumptions once held sacred. And in that sense, the gravastar has already fulfilled part of its purpose. It reminds us that the universe still holds mysteries vast enough to demand both humility and wonder. Somewhere, perhaps hidden in the heart of a galaxy, the answer waits, silent, immense and shimmering just beyond the edge of our instruments. No revolutionary theory in physics emerges without resistance, and the gravastar is no exception. While the idea has inspired fascination for its elegance and audacity, it has also drawn skepticism from many corners of the scientific community. The objections range from technical criticisms of its mathematical assumptions to broader doubts about whether such objects could ever exist in nature. At the heart of this debate lies a simple but important question. Does the gravastar explain more than it complicates? For many physicists, the first concern is plausibility. The gravastar model depends on the existence of exotic matter substances with negative pressure and energy conditions that violate classical physics. While such behavior is theoretically allowed in quantum field theory, it has never been observed in macroscopic amounts. Critics argue that invoking an unconfirmed form of matter to solve the singularity problem may simply be trading one mystery for another. They caution that the theoretical machinery supporting gravastars relies on finely tuned parameters, the pressure and density of the vacuum core, the precise thickness of the shell, and the exact balance between inward gravity and outward repulsion. A small deviation in any of these could destabilize the entire structure. Some researchers claim that such delicacy makes gravastars physically unrealistic, since nature rarely produces systems requiring perfect equilibrium to survive. Another major point of contention concerns formation mechanisms. While Mazur and Mottola outlined how a collapsing star might transition into a gravastar through a phase change, the details of this process remain speculative. Critics argue that no clear physical trigger has been identified that could cause matter to convert into vacuum energy under the extreme pressures of stellar collapse. Computer simulations of gravitational collapse grounded in general relativity consistently show the formation of event horizons rather than stable shells. Without a concrete demonstrable pathway from star to gravastar, many astrophysicists remain unconvinced that such objects could arise naturally. There is also the issue of observational indistinguishability. Even if gravastars exist, their external appearance mimics that of black holes so closely that detecting differences may be nearly impossible. Skeptics warn that this makes the theory unfalsifiable in practice, a cardinal sin in the philosophy of science. If no measurement can conclusively prove or disprove their existence, then, critics ask, can gravastars be considered part of empirical science at all? Defenders of the idea respond that the same criticism once applied to black holes themselves, which were purely theoretical for decades before observations confirmed their presence. The inability to test an idea today, they argue, does not mean it will remain untestable forever. Still, the burden of proof lies heavily on those proposing such radical alternatives. Some opponents also question the motivation behind the gravastar model. Black holes, they point out, already explain observations with remarkable precision. From gravitational lensing to the dynamics of accretion disks and the merging signals detected by LIGO, all available data align with the predictions of general relativity. Introducing gravastars, they say, risks overcomplicating the picture without providing clear empirical benefits. In their view, singularities and event horizons may not be signs of broken physics, but simply indications that our theories have limits of applicability boundaries of knowledge, not violations of it. To them, trying to replace black holes entirely may be unnecessary, perhaps even misguided. There is also a more philosophical critique that the gravastar is too tidy. Nature, in its complexity, rarely conforms to idealized symmetry. The gravastar's near-perfect equilibrium, with its precisely balanced shell and uniform vacuum interior, strikes some scientists as an artifact of mathematics rather than a genuine feature of the cosmos. The universe, they argue, thrives on imperfection. Stars pulsate, galaxies collide, and quantum fields fluctuate chaotically. A perfectly balanced gravastar, in contrast, feels almost contrived. This aesthetic discomfort, while not a scientific argument, reveals how deeply intuition shapes the acceptance of new theories. Yet not all criticism is dismissive. Even skeptics acknowledge that the gravastar serves a valuable role in provoking thought. It forces physicists to confront unresolved tensions between relativity and quantum mechanics. By showing how an alternative could, in principle, avoid singularities and preserve information, it highlights the limitations of current models and stimulates new lines of inquiry. Some researchers who once rejected the gravastar outright have since incorporated aspects of its framework into broader discussions of quantum gravity and vacuum dynamics. In this way, The controversy itself becomes productive, a sign of a field still alive with debate and curiosity. The sociological dimension of this controversy is equally revealing. In physics, as in all science, ideas compete not only through equations but through persuasion, reputation, and timing. Black holes, now supported by decades of evidence and public fascination, occupy a cultural as well as a scientific stronghold. Challenging them requires not only data, but narrative, a compelling alternative that captures imagination without losing rigour. The gravastar, though elegant, has yet to achieve that equilibrium. To many, it still feels like a mathematical construct searching for a universe that fits it. Yet this tension is precisely what drives progress. Every established idea began as heresy. When Einstein first proposed curved space-time, it too seemed implausible. When quantum mechanics emerged, its probabilistic nature outraged deterministic thinkers. The gravastar sits in that same liminal space too speculative to be accepted, too intriguing to be ignored. Ultimately, whether the criticisms prove fatal or merely temporary will depend on evidence. If future observations reveal echoes, surface radiation, or deviations from expected black hole behavior, the skeptics will have to revise their doubts. Until then, the gravastar remains a hypothesis in waiting, a mirror reflecting both the ambition and the caution of science. Its controversy is not a sign of weakness but of vitality, a testament to the restless curiosity that keeps humanity questioning even its most cherished truths about the cosmos. Every great idea in science passes through stages: ridicule, resistance, and eventual absorption into the collective understanding of humanity. The gravastar, whether it endures as a cornerstone of astrophysics or fades as an elegant speculation, already occupies a meaningful place in that tradition. It stands as both a challenge to orthodoxy and a symbol of how science evolves, not through certainty but through daring questions. Even if future evidence favours the classical black hole, the gravastar will have served its purpose by stretching imagination and forcing physicists to reconsider what lies beyond the familiar edge of theory. Its legacy, then, is not only about what it explains but about the intellectual space it opens. To appreciate this legacy, one must see the gravastar within the broader arc of cosmological thought. For centuries, humans viewed the heavens as fixed, eternal, and perfect. The discovery of evolving stars, expanding space, and the violent births and deaths of celestial bodies shattered that illusion. Each new theory has carried us further from simplicity and closer to a dynamic vision of the universe alive, changing and self-correcting. The gravastar continues that trajectory. It embodies a cosmos that avoids collapse not through intervention, but through the subtle play of its own laws. It suggests that even destruction follows patterns of renewal. In this sense, the gravastar represents the maturity of scientific thought, an acknowledgement that nature's elegance often hides within its paradoxes. The continuing study of gravastars also reflects a shift in how science operates in the 21st century. The line between theory and observation grows increasingly blurred. Advanced simulations, gravitational wave detections, and multi-wavelength imaging all intertwine, producing a picture of the cosmos more intricate than any single discipline could construct. In this environment, even speculative ideas gain legitimacy if they stimulate new ways of looking. The gravastar, by offering an alternative framework, drives innovation in modelling, detector sensitivity, and data analysis. It forces researchers to refine the precision of gravitational wave templates, to rethink the thermodynamics of compact objects, and to explore the physics of vacuum energy more deeply. The result is progress, regardless of the theory's ultimate fate. Its influence extends beyond science into culture and philosophy. The black hole has long dominated the imagination as a symbol of annihilation, a devourer of worlds, an end without return. The gravastar tempers that image with something gentler yet no less profound. It portrays the universe as self-balancing, capable of turning collapse into structure. In literature, art, and even popular media, such imagery reshapes how we visualize cosmic death. The black hole becomes not the grave of reality, but a gate to transformation. This subtle shift in metaphor mirrors the way humanity's understanding of itself evolves. Where once we saw chaos and destruction, we now glimpse symmetry and renewal. In this way, the gravastar transcends physics. It becomes a story about resilience written in the language of the cosmos. The idea's future depends, of course, on evidence. Over the coming decades, As new instruments come online, next-generation gravitational wave observatories, ultra-sensitive telescopes, and space-based detectors, humanity will look deeper into the shadows of the universe than ever before. The Event Horizon Telescope will refine its vision. LISA will listen to the cosmic symphony of merging giants. Somewhere in those observations, faint echoes or subtle reflections may reveal whether gravastars truly exist. Even if no such signals appear, the search itself will illuminate new aspects of physics. Just as the hunt for ether paved the way for relativity, the search for gravastars may uncover something entirely unexpected. Perhaps it will reveal new states of matter, new behaviors of space-time, or a more complete picture of how gravity and quantum mechanics intertwine. In this sense, every outcome is a discovery. Another enduring aspect of the gravastar's legacy is its reminder that humility lies at the heart of science. The theory refuses to accept singularities, not out of arrogance, but because infinities signal a failure of understanding. It embodies a conviction that the universe, however complex, remains intelligible. This humility is itself a kind of faith not in dogma, but in the continuity of reason. The gravastar tells us that no problem is unsolvable, only unfinished. It affirms that the cosmos is not an adversary to be conquered, but a dialogue to be understood. Future generations of scientists will likely revisit the gravastar with tools far beyond what we possess today. Whether they find confirmation or contradiction, they will inherit from this idea the courage to question and the patience to refine. That is how science advances, by standing on the shoulders of theories that dared to reach higher, even when they stumbled. In this way, the gravastar joins a long lineage of visionary concepts that shaped physics, some validated, others absorbed, none wasted. Its contribution may lie less in being correct than in being catalytic. As our telescopes grow sharper and our equations more precise, the boundaries between the conceivable and the real continue to shift. The gravastar occupies that twilight zone where speculation and discovery merge, a reminder that the unknown is not a void but a promise. The universe is still writing its story, and theories like the gravastar ensure that we keep reading, questioning, and imagining. Whether it endures or evolves into something new, its spirit will persist wherever curiosity dares to challenge finality. In that sense, the gravastar's true legacy is not confined to astrophysics. It belongs to the human impulse to seek meaning in the stars, to look into darkness and find, not emptiness, but the quiet pulse of creation still unfolding.